So good morning, everybody, and welcome to the presentation of my master thesis, which is titled Vision-Based Robot Gripping of Surgical Instruments for Intraoperative Assistance with Deep Learning Methods. First of all, I would like to show you the structure of this presentation. It includes 6 different sections, and those are introduction and motivation, definition of the problem, system description, detection algorithm, searching, localization, and gripping, and finally conclusions and recommendations for future work. Regarding the introduction and motivation, it can be said that this project consists of a first step towards the development of a functional scrub nurse robot, that is, a robot that can provide assistance to surgeons during a surgical procedure. Among the relevant tasks that were addressed during this work, we have detecting, locating, and gripping of surgical instruments. Also, among the advantages of the use of these systems, we have the economical aspects that on the long run, the use of these systems can be more cost-effective than hiring a human nurse. And also, they provide reliability in the sense that they can operate even during staff shortages. Regarding the problem that was addressed, it can be summarized as follows. Given a set of instruments and a laboratory setup, the goals were to identify the instruments within the images, locate the instruments on an instrument table, and grip the instruments using a robot manipulator. I would like now to describe the system I worked with, and you can see it over here in this image. It includes six different main components, and those are first the robot, which corresponds to the KUKA LBR robot that is located at the medical lab of the institute. I also work with stereo system. You can see it over here attached to the robot send effector. Also an instrument set that you can see over here in the table, an electromagnet that was used as a gripper, some 3D printed holders that allow to attach the components to the end effector, and finally an external computer in which the implementations and the code were created. I would like to specifically describe these 3 because they are especially interesting for this project. Regarding the stereo camera system, I like to refer to this as a system because it includes 4 different devices, and those are the infrared cameras, calculation of the depth of the scene, and also a point cloud of the scene. We also have an infrared projector that projects a pattern of infrared light that helps improve the accuracy of the calculation of the depth. And finally, we have an RGB or color camera that provides the color information. We can see the outputs of each device over here. The top images correspond to the left and right infrared images. You can see the pattern of infrared light that I mentioned before. The bottom images correspond to, on the left, we have the color image, and on the right, the depth information depicted as a color map. In this particular case, the color orange corresponds to points that are closer to the camera, and the color yellow to points that are far away. Please note that between these 2 images, there is not a pixel-wise correspondence, and you can see that, for example, if we concentrate on the chair, the pixels that describe the chair in this image are not the exact pixels that describe the chair in this other image. So in order to use both pieces of information, that is color and depth, they need to be matched together. And I did that by applying an alignment operation. You can see that over here. Here we have the aligned color image and the aligned color map. In this case, you can see that there is a pixel-wise correspondence. Regarding these black artifacts, they correspond to points of the scene for which the calculation of the depth was not possible, either due to occlusions or very bright areas of the scene. Now, regarding the instrument set, it was provided by Dr. Simon Spalthoff from the Hannover Medical School, and it corresponded to the instrument set for wisdom teeth extraction. It included 18 different instruments. You can see the names over here, but since the name were not particularly relevant for this work, I decided to rename them from instrument 00 all the way to instrument 17. And you can see a picture of each of them over here on the right. Now, regarding the electromagnetic gripper, you can see it here, as well as the complete assembly at the robot send effector. It was selected, the electromagnet was selected as gripper because it was expected to provide a robust grip. It was manually activated. I did that using a button just to simply close an electrical circuit. and its specifications indicated that it was powerful enough to lift the instruments. It is now time to talk about the detection algorithm, and the selected algorithm was mask region-based convolutional neural networks, or mask RCNN, which is an algorithm that is meant to perform a task known as instance segmentation. The idea is that given an RGB image, the algorithm will provide an output that includes the bounding boxes, the masks, the labels, and the class scores of every single instance of every single object of interest in a particular scene. As it is common, or it is a rule in machine learning or in deep learning algorithms, it requires a data set. So an initial data set was created that is using RGB images and their corresponding ground truth masks. This initial data set included 1,044 images. 225 of those were manually labeled image and were part of the training set. These were artificially augmented using flips, and with that, the test and validation sets, 72 images were used for each, and two interesting aspects were found, and those are that labeling requires a lot of time and effort, and initial tests indicated poor performance of the algorithm. So in order to address this, I decided to propose what I like to call the MBOI method, which stands for mask-based object insertion, and it's a method for data augmentation. The idea is that using a set of background images, a set of single instrument images, their corresponding ground truth masks, and the 3D information provided by the camera, the method allows us to obtain artificially augmented images and their corresponding artificially augmented ground truth masks. So the idea is that using this information that is relatively easy to obtain, since labeling a single instrument image is considerably easier than labeling a multiple instrument image, we can generate artificially augmented multiple. Important is that using 3D information, the relative size of the instruments can be preserved. I would like now to describe this method. You can see it over here. So given a background image, there is an image of just the tissue where the instruments are supposed to be lying, a set of single instrument images and their corresponding ground truth masks. The initial step is to extract the pixels that correspond to the actual instrument. We then apply a randomized similarity transformation, and we then insert the pixels into the background image. And as you can see, several instruments are inserted in order to generate a multiple instrument image. These steps can be applied not also for the color pixels, but also for the masks, in order to generate the corresponding ground truth mask of this artificially augmented multi-instrument image. So the idea is that with this information, we can generate thousands of images that are part of our data set. Initial results look like this. Please note that on the left, the instruments appear to have a contour of black pixels that comes with the insertion process. So in order to improve the quality of this image, I used a post-processing step that reduces them a little bit or eliminates them completely. And this is an example of the final result of an image obtained using this method. I decided to enhance the previously presented dataset. You can see it over here. All of these subsets are the same as before, but I added this 2,500 images generated through these MBOI method, and I included them into the training set. So we now have two different data sets, and I decided to train two different versions of the mask RCNN algorithm, one using just these sets and one using the complete data set that you can see over here. And I compared both of them in order to test how effective the use of these images was. In order to do this comparison or this evaluation, I decided to rely on the confusion matrix and the intersection over union, or IOU metric. The confusion matrix is basically a table in which we have, on the rows, we have the true labels of the pixels, and on the columns, we have the predicted labels. Something important is that the entries on the main diagonal indicate the performance of the algorithm in such a way that the higher the entries on the main diagonal the entries on the main diagonal are, the entries on the main diagonal are, the better the performance of the algorithm. Regarding intersection for both masks and bounding boxes, and given a prediction and a ground truth, the idea is to divide the area of the intersection over the area of the union, and we obtain a numerical value that in the ideal case, it's a value of 1, that is a perfect prediction, and in the worst case scenario, we obtain a value of 0. With this, two versions of the algorithm, that is without the use of the MBOI method. I would like us to concentrate on the main diagonals of these confusion matrices. Please note that there are some low entries and some low value entries and some high value entries. But in general, the entries of the version 2 are considerably higher than those of the version 1. That indicates that the MBOI method provides a better performance. And because of this, it was used for later steps of the project. Using this version, I decided to evaluate the performance on both the prediction of the masks and the prediction of the bounding boxes. And here we have the IOU metrics for every class, but the results can be summarized in mean IOU values. Please note that the value for the bounding boxes is considerably higher than that for the masks. And because of this, I decided to rely on the bounding boxes for the localization of the instruments. Now it is time to talk about the search localization grouping. This required a previous step, which is the hand-eye calibration. It is basically a procedure that allows us to obtain the homogeneous transformation matrix between an end effector coordinate frame and a camera fixed coordinate frame. The typical equation for this procedure is this one over here. It includes 3 different matrices. Matrix B, which is the homogeneous transformation matrix between the camera coordinate frames for a given robot pose J and a robot pose I. Also, we have the matrix X, which is basically what we are looking for, which is the transformation between the end effector and camera coordinate frames. Then the matrix A, which is the transformation between end effector coordinate frames for pose J and for pose I. And the idea behind this is that we want to form a point that is depicted in camera coordinate frame. We want to depict it into the inertial coordinate frame that is located at the base of the robot. For that, we require all of these pieces of information, which are obtained from the camera system. The point in the camera coordinate frame is obtained from the stereo camera system, the matrix X, from the hand-eye calibration, and this transformation matrix is obtained from the internal sensors of the robot. And with this, the transformation that we were looking for was found. Now, regarding the searching strategies, I decided to propose 2 of them. And the first one is which is quite straightforward. The idea is that the user provides request via keyboard that activates the motion of the robot. The robot goes to a left searching position in which the detection algorithm is activated. If the desired instrument is detected, then the robot will approach it and grip it. And if it doesn't, it will advance to the right searching position. Again, the detection algorithm will be activated. And if the instrument is detected, the robot will approach it and grip it. And if it doesn't, then the search concludes and the request is considered unsuccessful. That is the online searching approach. The second one is the offline searching approach, which consists of 2 phases. The first one is the searching phase, which is basically gathering of information. And for this case, 3 different searching positions were defined: the left, center, and right searching positions. For each of them, 3 frames were taken and recorded, as well as the detection information and the 3D information provided by the camera. The system then performs a calculation phase in which the goal is to create a location map that is a virtual space that corresponds to the table. So the idea behind this is that these bounding boxes are mapped into a common virtual space that corresponds or represents the actual space on the table. We can see that over here. Here we have the location map for the first frame, second frame, and so on. Please note that if we put all of these location maps on top of each other, several bounding boxes will overlap, and several overlapping bounding boxes will indicate the presence of an instrument, and the label of that instrument will be the most common label among all of the overlapping bounding boxes. And with that, the method comes up with a final location map that represents the locations of all of the instrument in the scene. We can see that over here. On the left, we have the actual scene, and on the right, the location map. These check marks indicate the correct assignment of the labels, while the X's indicate incorrect assignments. Please note that only 3 of them are incorrect in this case, which is quite a good result. And with this, we can now compare the online and the offline searching approaches. I did that by using these confusion matrices. What I did here is I used 10 different instrument arrangements on the table, and I requested each instrument once. And with that, I created these confusion matrices. On the rows, we have the requested instrument, and on the columns, we have the localized instrument. And again, we can concentrate on the main diagonals. Please note that for most of the instruments, the entries are quite high. The results can be also seen in this table. And for a quick comparison, we can concentrate here, which for a total of 143 correct localizations were made by the offline searching approach, sorry. And for the case of the online, only 129. That indicates that the performance of the offline searching approach is better, but it comes with the trade-off that it requires the initial searching and calculation phases, which are quite slow. They take some minutes, and also they are sensible to changes in the arrangement of the instruments. So there is a trade-off between the two methods. Regarding the gripping, the use of electromagnet as a gripper was associated with some advantages. It was determined that it was robust, simple, and it provided more than enough force for lifting the instruments. But nevertheless, some disadvantages were found, and those are that some of the instruments include non-magnetic parts, which makes it impossible to lift them sometimes. Also, the magnet has a reduced manipulation capacity, and that is due to the fact that the grip is only from the upper surface of the instrument, and it can sometimes it doesn't provide the dexterity that some tasks could require. For example, future tasks such as cleaning the instruments could not be performed using this gripper. And finally, the use of the electromagnet was associated with residual magnetism that sometimes hinders a successful release of the instruments. Sometimes they get stuck to the magnet even when the magnet is deactivated. And now I would like to show you just a quick demonstration. In this case, this is the desired instrument, and I will be demonstrating the performance of the online searching approach. Here in the video, I am providing the keyboard, the input, the online searching approach. Here, the desired instrument cannot be seen by the camera, so the robot will move from the left searching position to the right. In this right searching position, the instrument should be visible. It takes a little bit of time because my computer is not that powerful. But after the detection is successful, the robot will approach it. It will then grip it and goal location, which is this to the home pose. I would like to state the conclusions of the project. It can be said as a success. The goal of developing a scrap nurse robot was achieved. It was found that the proposed MBOI method allows for generating data that can improve the performance of the detection way. Also, both searching strategies allow for a successful location for most of the instruments. And finally, the electromagnetic gripper is not optimal for this application. Regarding the recommendations for future work, increase the number of manual images. That is always a possibility with deep learning methods. And it will be especially important to focus on instances of instruments that, or of including instances of instruments for which the performance is not optimal. Something advisable would be to design or select a gripper that is more for this application. If we do this, it could be necessary to improve the performance associated with the prediction of the masks, because the mask will provide a better description of the geometry of the instruments. And finally, the use of a more powerful computer would be advisable in order to reduce the time taken by the detection task. And with this, I conclude this presentation. Thank you very much.
Yes, thank you very much. Also from our side for this interesting insight into your presentation and of course your master's thesis. So are there any questions? I think we have time for 2 or 3 short questions. Okay, so maybe I start with a quick question. So coming back to the reliability of the instrument recognition, you use one camera, right, which is mounted on the tool center point or near the tool center point or on the flange of the robot.
Yes.
So from your experience gained during the project, would it help to use a second camera, probably, and then fuse the information, or what other ideas do you have to increase the detection quality?
The detection quality. So, to be honest, I don't think using another camera would help. I believe the problems. Okay, can you hear me? Sorry.
Yeah, fine.
Yeah. Okay. Okay. So, I think the problem with the detection, as you can see, maybe let me just find where it was. Over here. Yeah, the problems with the detections are more associated with the data set, because what I believe is that the amount of data that I used, like the amount of original data, not the artificially augmented data, it is not that big. It is a total, I believe, 380 images.
Okay.
And out of those, I artificially augmented them. So I did not use more because of the time constraint, but I believe we can obtain better results by focusing, for example, in these particular instruments that look quite similar, and that's why the detection is not the best. But I do believe the problem regarding the detection is with the data set and not associated with the use of or with the lack of another camera.
Okay, thank you. So, further questions?
I would like to comment on the previous question. The problem with the low detection rate, already said that is especially the case for the instruments that look very alike, and the robot has to move the camera towards the instrument to see the subtle differences between 2 kinds of instruments, and therefore we think that an external camera, where the distance to the instrument table is even larger, would not result in a better detection score.
And if you change the trajectory when you approach to the instrument, so take pictures from the instrument from different angles of view, would this probably help?
I believe I did that, but I believe if it could help, but it's something that I already tried. It's not that I didn't try that already. In the artificially augmented images, they were taken not from let's say a perpendicular angle, but from oblique angles too.
Okay, thank you.
Maybe just a comment on that. The more problematic instruments were these over here, like example, an instrument 14, and as you can see, they are very similar to each other. Maybe you can't even tell the difference. Yeah. So, and also these pincers. So there's a reason why they are problematic, because they look very much alike. Yeah.
Okay, maybe one last question.
Yes, I would have a small question regarding the alignment of the instruments on the table. Is there any method that you can think of to handle occlusion or instruments that are put on top of each other?
Oh, that is something I didn't consider in this project. I knew it would be something that will increase the complexity, but I didn't consider that until now. And as you can see, for example, this is just an example of an artificially augmented image. These, for example, I specifically developed the algorithm in order for them not to overlap, because I was trying to limit the cases. I mean, the arrangements in the table are usually not overlapped. They are usually arranged somehow so I did not consider occlusions. But with occlusions, I believe this method can also work. Like, you can imagine this inserted instrument over here. So I think this MBOI method can also be used for generated artificially augmented data with occlusions. So I haven't tested it, but I think it could help in order to address that scenario too.
Yeah, and as you said, I think in surgical applications, the instruments are not really aligned on top of each other, so it's not really a realistic use case.
Exactly. That's what I thought at the beginning of the project. Yeah.
Okay, then I think we are a little bit running out of time, as we have a second student waiting, right? As far as I know. So once again, thank you very much for your presentation.
Thank you. Thank you for your attention.
We are looking forward for the future cooperation. Bye-bye.
Me too. Bye.